right, I want to talk quickly here about logarithmic differentiation. This is a more advanced type of derivative, and so if I put this on the test, it's going to be an extra credit question. But it does combine a lot of the information that we've been talking about, so it's a good problem to look at. Plus, you wouldn't be able to do these derivatives any other way. So sine of x to the x, we can't use a power rule because there's not a number up in the exponent. And we can't use an exponential rule because there's not a number down in the base. So this would be impossible to do without this technique. What we're going to do is we're going to take advantage of the properties of logarithms, and we're going to take the natural log of both sides. Natural log of y equals the natural log of sine of x to the x. And what this is going to let us do is we're going to be able to get rid of the exponent, because one property of logarithms is that if I have a natural log like this, I can take my exponent, my x, and bring it out in front of my logarithm. So this is the same as x times the natural log of sine of x. So now that we have that, we can use some implicit differentiation. So now we're going to take our derivatives. We've got 1 over y dy dx, since we took a derivative of y, equals, and now we have a product rule. It's going to be first times derivative of the second. Well, derivative of natural log of sine of x, derivative of natural log here is going to be 1 over the thing, so 1 over sine of x. But then since sine of x is inside of the natural log, we need a chain rule. Times derivative of the inside part. Derivative of sine of x is cosine of x. Plus second times derivative of the first. So natural log of sine of x. And then derivative of x is 1. So now we can start to do some simplifying here, because I know that cosine of x over sine of x, cosine over sine is cotangent of x, and then times 1 is just going to be itself, so natural log of sine of x. And then I want to solve and get dy dx by itself, so that means I need to multiply by y on both sides to say that dy dx equals y times this whole thing. And so our last step is going to be, I don't like this y here. I want to be able to write this just in terms of x. And all we have left is a y here. Well, this y, we know what y is in terms of x because it's right here. Y is sine of x to the x. So we're going to take sine of x to the x and put it in for y. So dy dx is going to equal sine of x to the x times all the rest of this. And that's going to be our final answer. So just to recap everything that we did here, the key step, which I'll show a couple more times here, the key step is that when we take the natural log of both sides, we can use the properties of logarithms to make this a more doable derivative. But because we took the natural log of y, that means we need to use some implicit differentiation. And then once we get y over to this side, we plug in the actual function so that it's all in terms of x. So let's do this for a couple more of these. I'm not going to do the whole thing on the rest of these. I'm just going to show the first couple steps so that you can recognize where we're going to use it and what it looks like. So y equals x to the natural log of x. Once again, I can't do this our typical way. So what we're going to have to do is the first thing we're going to do is take the natural log of both sides. Natural log of x to the natural log of x. And then what I can do is I can say natural log of y equals this natural log of x can come out in front. And then I just have a natural log of x left inside of there, since I took the exponent out in front. And then we would do implicit differentiation. 1 over y dy dx equals, to take this derivative, you can either do a product rule. You could say this is natural log of x times natural log of x. Or you can also say that this is natural log of x quantity squared and do this as a chain rule. So whichever one you're more comfortable with here, you can do this as a product rule or a chain rule. But either way, at the end, you do the same thing. Multiply by y on both sides, and then substitute it for x times natural log of x. So those would be your first couple steps. So I'm going to show you one more here. This one's going to be fancier. And this one is actually not impossible to do without this technique, but it's going to be a whole lot harder. Because if I were to do this all in one go, here's what we would do. This is all to the 1/5. This is all to the 1/5 because that's the fifth root. So we would need 1/5 times this whole thing to the negative 4/5. But then since I was all to the 1/5 and I still have things inside of the function, I would need a chain rule. So I'd have to multiply by the derivative of the inside part. Well, bad news. The derivative of the inside part here, so times derivative of the inside part. Bad news, derivative of the inside part is a quotient rule, is one giant quotient rule. So then we would have low 5 cubed d high, derivative of the top. Well, that's a product rule. And then when you get to the derivative of the first, then it's a chain rule inside of that product rule. Inside of a quotient rule, inside of another chain rule. Okay, let's do it a different way. Let's take the natural log of both sides. So it would not be impossible to do the other way, but it would be very long and tedious. So instead, we're going to say this is the natural log of all of this to the 1/5 power. And we're going to do a whole lot of simplifying before we start to take the derivative here. To the 1/5. And the reason we want to do that is because then we can take this 1/5 and bring it out in front of the natural log. So that now we don't have to worry about that chain rule. We just have this 1/5 out in front. But we're actually going to end up being able to make this even simpler, because we've got a property of logarithms that, since we have a whole bunch of multiplication and division here, you should remember that the log of a times b is the same as the log of a plus the log of b. That's another property of logarithms. So we can make this even simpler using those properties of logarithms. And then we have a same one for division, that the log of a divided by b is the log of a minus the log of b. And that's related to our properties of exponents. So what that means is that we can separate this out into separate logarithms with addition. And addition is a whole lot easier to talk about than multiplication when we take a derivative. So that's going to give us the natural log of x minus 3 squared plus the natural log of x squared plus 1. And then since we have a division, then we're going to have a minus the natural log of 2x plus 5 cubed. Good news! We can make this even easier because now we have a bunch of exponents inside of a natural log. And when we have a bunch of exponents inside of a natural log, that means we can take those exponents and bring them out in front. So I can put a 2 out in front of here. And then I have to leave this how it is. But then in my next one, minus, I can take this 3 and bring it out in front. And this is still a little complicated to take the derivative of. I still have a couple chain rules in here that I have to deal with, but it is nothing like it was at the start where I had chain rules inside of product rules, inside of quotient rules, inside of other chain rules. So, a lot more straightforward things to deal with here. So that's logarithmic differentiation. It's using the properties of logarithms to make the derivative more manageable to work with. So that's all I have for you for now, and I'll talk to you more soon.